In the Unit 2, I will introduce some progresses in the development of intelligent and connected vehicle, ICV, in China. The safety impact and some research ideas will be discussed. Artificial intelligence is an important force in the new round of scientific and technological revolution and industrial transformation, accelerating the development of the new generation of artificial intelligence is a strategic issue concerning whether China can seize the opportunity in the new round of scientific and technological revolution and the industrial transformation. The China government is making great efforts to encourage and promote the development of AI-related industries, among which intelligent and connected vehicles is an essential one. We set up a national long-term plan for ICV industry. By 2025, proportion of vehicles with driving assistance or partially automated or conditionally automated should be greater than 80%. Partially automated or conditionally automated should reach 25%. By 2030, driving assistance rate and connected vehicle rate will be close to 100%. High or fully automated vehicle rate should be 10%. This is an overview of the major milestones for ICV developments. In 2003, CLV, developed by the National University of Defense Technology in China, has created the world's fastest speed of 170 kilometers per hour. In 2009, we held the first China Smart Car Future Challenge competition. In 2015, M-City in Michigan became the world's first CAV pilot zone in operation. In 2016, China's first national smart connected vehicle pilot, the pilot closed field test zone, was put in operation in Shanghai. In 2016, Tesla became the world's first automaker to mass-produce fully autonomous driving hardware. In 2016, the Google Driverless project has declared its independence and created a new company called Waymo. April of 2017, Baidu announced the Apollo project, becoming the world's first autonomous vehicle technology company to announce the opening of its own technology and platform. In May, South Korea and Germany have introduced laws allowing driverless cars to be tested on roads. July, Audi has unveiled its flagship 2018 model, the A8, which it says it is the first L3 class production car to be developed for autonomous driving. December, Beijing has become the first Chinese city to open public roads for autonomous driving tests according to regulations. In March of 2018, Shanghai has issued the country's first open road test license plates for intelligent connected vehicles. April, 3 ministries and the commissions of China issued the test management standards of intelligent connected vehicles for trial implementation. And Zhu, Changsha, Xiangjiang, Liu Street intelligent network system test area opened into operation. In December, Waymo launched the driverless taxi payment service and started the process of intelligent connected vehicles commercialization. Later on, the development of ICV grew vigorously. By 2020, China has more than 20 demonstration zones for testing intelligent connected vehicles. The ICV industry is developing rapidly, and the ICV industry market will be $29 billion. For example, the national ICV Changsha testing zone covers an area of more than 820,000 square meters with 228 testing scenarios. In Changsha, 135 kilometer urban roads and 100 kilometer expressway are employed for ICV testing. In addition, a smart bus demonstration line was built. More than 20 well-known enterprises came to cooperate. Changsha ICV industry has got more than 2.3 billion renminbi financial support from Changsha government. Road safety research is now moving into an increasingly scientific and cross-disciplinary phase. And ICV development may dramatically improve the safety of road traffic. Nevertheless, toward the potential safety impact brought by ICV, there are currently so many questions in hand to answer and to resolve. Let us go back for the historical phases in traffic safety research. During the early days of motorized transportation, accidents were seen as a result of backlog, and the research was focused on describing what happened and on collecting basic statistics. When the number of accidents started to increase, the view that a small number of drivers could be responsible for the majority of accidents arose, and the term accident proneness became in vogue. Research focused on finding the characteristics of such accident-prone drivers and who were to blame for causing accidents, and a search for psychological testing as a predictor of accident-prone drivers started. In the next period, from roughly 1950 until 1970, the more dominant view can be characterized as looking for the cause of accidents. One cause per accident is postulated, either the road user or the vehicle or the road, and solutions were sought in a choice from the 3 E's: engineering, education, and enforcement. In the 1960s, 1970s, and the 1980s, more emphasis was put on technological improvements of vehicles and roads. This period is characterized by a multi-causal approach. It's not a single cause, but a combination of factors that contribute to the occurrence of an accident. During this period, the so-called Harden matrix was introduced, showing multiple factors and stages of the accident. In more recent years, crashes are viewed as the result of integral road system. The view that the road system should be adapted to human capabilities and limitations becomes a more and more commonly recognized idea. People characterizes the period from 2000 onwards by a better implementation of existing policies and the systems management perspective, such as sustainable safety in the Netherlands and Vision Zero in Sweden. Researcher points at the notation that the term system replaces driver for most failures. In more recent thinking, the driver, vehicle, road system. In summary, the safety concern for road traffic has experienced several stages, from reactive safety to proactive safety to interactive safety, with which a variety of automated driving assistant functions are available. With challenges of the emerging technologies of ICVs, we will come into a new stage of automatic safety. Future transportation system is expected to be a smart, fast deliver, and eco-friendly system based on big data and AI technologies. As a vital part of the intelligent and collected transportation system, ICVs are expected to provide safer, more efficient, more environmentally friendly, more convenient services and comprehensive solutions, which is commonly recognized as the future developing directions. Recently, remarkable processes have been made related to technologies, regulations, and supporting facilities in the feasibility and practicality of ICVs. However, there are still many challenges in the research field of operational safety technologies of ICVs. As most of the audience are students, we present 5 major challenges and problems here for the purpose of idea exchange. First, from traditional traffic crashes to ICV safety. How to use crash analysis methods to provide theoretical, technical, and data support for the development of ICV safety, based on recognition of the mechanism of existing traffic system crashes. Second, from environmental perception to risk judgment. In-vehicle and roadside infrastructures could drastically strengthen ICV's environmental perception capability. The challenge is how to intelligently match the driving scenarios and the crash risk and determine the risk level of the real-time scenarios. The third, from intelligent decision to vehicle responses. The intelligent perception and rapid decision capability of ICVs based on vehicle engineering technology should be re-examined. The challenge is how to comprehensively upgrade the vehicle proactive, passive response safety protection system to improve the safety of the road users. The fourth one, from countless scenarios to ICV testing methods. How to carry out more targeted scenario tests for traffic crashes, to develop testing methods with low cost, high efficiency, and high reliability, and to establish reasonable ICV test scenario databases and evaluation standards. The fifth one, how to operate ICVs in complex transportation system. Given the transportation environment with different market penetration rate of ICVs, the challenge is how to form the theories and methods of planning design and operation management and the information service for future transportation system. Well, in this lecture, we talk about typical urban ITS applications in China and the future transport system characterized by intelligent and collected vehicles. I would like end up with this lecture with some concluding remarks. The essential thing in transportation systems is to well maintain the equilibrium of transportation supply and the travel demand at different levels. Urban intelligent transportation systems are characterized by extensive sensing for the traffic operation conditions, integrated real-time information related to various transportation subsystems, big data analysis and decision-making simulation and evaluation, as well as subtly traffic guidance and control, etc. AI, cloud, and big data technologies stimulate the emerging of intelligent and connected vehicle technologies, and subsequently push the rapid evolution and formation of future transportation systems. Nevertheless, there are numerous research challenges and opportunities for theoretical and technological advances toward wide application in transportation system. This is all I want to talk in this lecture. Thanks for your attendance.